Well, all right, welcome back. You've made it to the tougher problems involving trig sub. Let's try some where we're going to use completing the square. So these are where the problems get fun. So let's say we've got the integral of x over the square root of x squared minus 6x plus 5 dx. How might I know to try completing the square? This doesn't look like one of the classic forms, right? I mean, classic forms have two terms in them. Either, the forms look like this, and my radical has three terms in it. So yeah, that's why I might try completing the square to get down to two terms. Okay, so what we want to do is group these terms together. Then we have to remember how to complete the square. Give yourself a little room to complete the square. Okay, so to complete the square, we want to take half of this and square it. So half of minus 6 is minus 3, and then we square it for 9. So we're going to add 9, and for balance, subtract 9. Okay, so the next thing I'm going to do is I'm going to factor this. So this will factor into x minus 3 quantity squared. This will be minus 4. And this is actually really nice because this is like a u squared, right? Variable stuff, u squared minus a squared form, which should remind you, so let's see here, u squared minus a squared form is exactly here, so we should be making a secant substitution. Pretty clever. Isn't that cool? Pretty clever. Okay, so we want to make a secant substitution here. All right, so to make a secant substitution, we're going to say u is equal to a secant of theta. Really, really neat. Well, because I need to find dx, let's get x by itself. So I'm going to add 3 to both sides like this. And then I can take the derivative carefully. Derivative of 3 is 0. Derivative of secant is secant tan of the same angle theta. So that seems really promising, right? Because I've got a replacement for x, I've got a replacement for dx, and I've got a replacement for this. So actually x, dx, and this. So that seems really nice. So we can completely go from the land of x's to the land of thetas. So there's 3 plus 2 secant of theta, and then dx. Okay, so that seems pretty good. And then down in the radical, we have the following. So here we have got the square root of, this should be 4 secant squared of theta minus 4. So if I want that, what I do is take this quantity and just square both sides. If I square both sides, that will allow me to replace this with 4 secant squared. So that seems pretty nice. So our next move is to factor out a 4 and then look for a Pythagorean identity. I'm going to hold off on any sort of distributing because I'm hoping, fingers crossed, that some things will cancel out and make life much, much nicer. So this seems good. We've got 2 secant of theta tangent of theta. D theta. That's over the square root of, we're factoring a 4 out. And that's going to give us secant squared of theta minus 1. Look at that Pythagorean identity right there. How nice is that? So that's good, right? Because we know that's equal to, what do you say, 4 tan squared. So let's note that. So we've got 3 plus 2 secant of theta times 2 secant of theta tangent of theta d theta. And then in our radical, this collapsed pretty nicely. Okay, so by Pythagorean identity, this is exactly this. But if we think about it, we're kind of clever about this. We realize that the 2 tangent will cancel with essentially 2 tangent. And again, we are taking theta, so that this is nice. So no worries. Everything is nice, nice. So that cancels, that cancels. Okay, so that seems nice. So that means I can distribute my secant that's left over. That'll go here and here. So that'll give me 3 secant of theta plus 2 secant squared of theta, d theta. And that we can just directly compute, right? Those are both famous calculus rules. So that's going to be a natural log. So this is 3 times the natural log of absolute value of secant of theta plus tangent of theta. And we know the antiderivative of secant squared is tangent of theta. That seems really, really nice. Tangent, tangent, tangent. There we go. Plus c, of course. And now we want to go from the land of thetas to the land of x's. And so let's see. We need a right triangle. And we've been saying this whole time that the key is to go back to your original substitution statement and solve for the trig function. So my original substitution statement had the 2 here. I just isolated the trig function. And so remember what that does for us. That allows us to make a right triangle. So here's theta. Secant's the flip of cosine, so that'll be hypotenuse over adjacent. And then I can use the Pythagorean theorem to find the missing side. And so that's x minus 3 quantity squared minus 4. That's my missing side. And I've got all the stuff I need to figure out secant of theta, which I have for free, and really tangent of theta. So this is 3 times the natural log of, well, secant of theta plus tangent of theta. Well, tangent is opposite over adjacent. Opposite over adjacent. And then plus 2 tangent. So here's tangent opposite over adjacent plus c. So let's write this as a single fraction, and we'll reduce the 2's. So this is 3 ln of x minus 3 plus the square root of x minus 3 quantity squared minus 4 all over 2 plus the square root of x minus 3 quantity squared minus 4 plus c. Okay, so there's one example of completing the square. I think that we should do one more. One more example of completing the square with trig sub. Okay, so here we go. Okay, so we've got the indefinite integral x squared over the square root of 2x minus x squared. And at first this seems promising because that's 2 terms, but remember in all the forms that one of the terms was purely constant, right? And neither of those terms is purely constant. That's what a means in these forms, purely constant, whether it's 25, a 100, a 7, a 3, a 1/2, a 4/3, but purely constant. Okay, so how do I get to one of these forms? Well, it's pretty clever. We're going to complete the square again. So if I complete the square, I want a leading coefficient on my x squared of positive 1. So let's factor out a negative. We'll factor out a negative 1. Okay, so that'll be negative 1 times x squared minus 2x. That seems pretty nice. So not only did I factor out a negative, but I switched the order, right, by the commutative law of addition. And so now let's give ourselves some space here. Now when we complete the square, we want to be really, really careful because this 1, or minus 1 rather, is affecting everything inside here. So we have to be really, really careful. Okay, so we know when we complete the square, we want to take half of this and square it. So half of this is minus 1, square it for plus 1. Here's where you have to be careful because did we really just add a 1 there? Since everything inside is affected by the minus 1, that's actually a minus 1. And for balance, I need a plus 1. So convince yourself. If I were to redistribute, that's actually a minus 1. And for balance, I need to add, the opposite, and there's plus 1. Okay, so what can we do now? We can factor and reverse the order. So let's write this plus 1 first. Let's write that there. And then minus this term, but factored. So that's x minus 1 quantity squared. So there's 1 minus this factored. That'll be pretty helpful. So now we have an a squared, because that's constant stuff, right? So we've got an a squared minus variable stuff squared form. And that's our first form, right? This is going to be a sine substitution. Well, that seems pretty good. Everyone likes a good sine substitution. So let's see what we have here. So we have this form that we want to fill in. Okay, so this is u squared, so u must be x minus 1. This is a squared, so a must be 1. Okay, so that's going to help with this. And then let's isolate x. So x is equal to 1 plus the sine of theta. And then I also need a dx. Don't forget the dx, please. So this is going to be cosine of theta d theta when I take the derivative. Okay, so let's plug everything in. So in for x goes this, in for x minus 1 goes this, and in for dx goes all of this. So we've got x squared, so x squared, we've got dx, and then inside of our radical we have 1 minus sine squared of theta. Okay, so yeah, because sine of theta went in here, so it'd be 1 minus sine squared. Okay, well, we realize something at this point, right? So we realize this is going to be cosine squared, which is cosine, which will cancel with that. So now let's expand this out. So how are we going to expand this out the classic way, right? So a plus b quantity squared is a squared plus 2ab plus b squared. Okay, so yeah, let's go ahead and expand that out. Let's see what happens. And maybe just for the sake of completeness, so you can see what I'm squaring, let's write that down. Okay, that seems fine. So we can square that out. That's going to give me, it looks like 1 plus 2 sine of theta plus sine squared of theta d theta. But notice we've got this standalone term with a purely even power, right? So we should use our power reducing formula. That's the formula that comes from double angle formula for cosine. So let's recall that. That's a really helpful thing to know. So that's equal to 1 minus cosine of a double over 2. Okay, so yeah, by the power reducing formula, this gives me 1 plus 2 sine of theta plus 1 minus the cosine of a double angle over 2 d theta. Next thing I'm going to do is factor out a 1/2. So from here, here, and here. So if I factor out a 1/2, you just ask yourself the following. So if you're confused, how do I factor a 1/2 out of those? Just say 1/2 of blank is 1. That's got to be 2, right? 1/2 of blank is 2. Must be 4. So it's not a big deal. And then I've got plus 1 minus cosine of a double. The over 2 is factored. D theta, notice the like terms. Well, it seems as though the worst is over because adding like terms, that'll give me 3 plus 4 sine of theta minus cosine of 2 theta. And I know how to integrate all 3 of those terms. So let's go ahead and integrate them. Antiderivative of 3 is 3 theta. Antiderivative of sine is minus cosine. And then here I'm going to get minus 1/2 sine of 2 theta. This will be plus c, but we've got a lot of work to do to go back to x's, right? So we need to go back to x's. Remember how to go back to x's. You go to your original substitution statement. That's this from way back at the beginning, right? So go back to your original substitution statement. And we want to somehow get a fraction out of it. So that's not too bad, right? We want to get a fraction out of that. So how do I get a fraction out of that? Yeah, we can just put that over 1. Okay, so this can just hang out for a second because we need to deal with this right triangle and then make a couple observations about a couple of the terms. Okay, so we've got x minus 1 equals sine of theta from our original substitution. Put that over 1 because you want to form a right triangle. So now you're in a position to form a right triangle because sine of theta is equal to opposite over hypotenuse. Okay, at that point, you can use the Pythagorean theorem to find the missing side. So that's going to give me 2x minus x squared if I square everything out. And now there's an issue because this triangle is in terms of 1 theta, not 2 theta. And doubling the sides does not do anything to the angles, right? If that were the case, you'd have a triangle with 360 degrees. So you can't just double the sides, right? You get similar triangles, but you don't get, that's not helpful. So instead, what you want to do is use the double angle formula for sine. So sine of 2 theta is 2 sine theta cosine theta. Okay, notice that the 2's will cancel. So the double angle formula for sine is really handy because this triangle is in terms of 1 theta. So that'll help. This triangle will now help here and here, but it won't help here. So how do I get rid of that 3 theta business? No problem. To get my hands, oops, that's not secant, it's sine. To get my hands on theta, I just take the arc sine, the inverse sine of both sides, because that's the function that will cancel out sine so we can get our hands on theta. Okay, no problem. So now we've got 1/2. So 3 theta. So 3 theta, that means 3 arc sine of x minus 1. Okay, so that's that. And then this we can get just from our triangle, no big deal. So 4 cosine. So cosine is adjacent over hypotenuse. So that'll be 4 times the square root of 2x minus x squared. And then minus, so sine's right here. So there's sine of theta times the cosine of theta. Well, cosine we said was radical 2x minus x squared. This is plus c. Quite a journey, but quite clever algebra. I really, really enjoy those integrals. Really, really fun.